Hi, Amanda English, cybersecurity major, and now we are picking back up on universal gravitational constant. So we are continuing on with Cavendish and his original experiment. Let me try to enlarge this. Okay, so his original torsion balance experiment was conducted in 1797 and 1798. And one of the items he used was a 6 foot wooden beam that was suspended in the center by a torsion wire, and it carried also two small lead spheres on it. And what he did with it was he calibrated the torsion constant by gently twisting the beam and measured its natural oscillation period. One of the hurdles that he had during this experiment um, was the gravitational attraction between the masses equated to mere microneutrons. Why he did the work, one of the main reasons was he was interested in trying to find the density of the Earth. And no one at that time had been able to measure tiny gravitational forces between objects in a lab. And so it was helpful because it immediately helped scientists find the first accurate value for the gravitational constant, or G, and allowed them to calculate the mass and density of Earth for the very first time. Okay, so in today's times, they use torsion balance with laser interferometry, which is more of an advanced version of the Cavendish method. And they use a thin wire and suspended masses, but they use laser interferometers to direct displacement. So they have better equipment, basically. Some of the differences in the approaches today would include visual observations and laser-based observations. Again, they didn't have that back then, or of course they would have used them, but technology has come a long way. So some of the benefits of this has been understanding planetary motion and orbits, and some of the future expectations of this technology will help us better determine planetary defense and space engineering. And that's it. Until next time, take care.
Lead masses, two heavy lead spheres suspended separately so they can be positioned close to the small spheres, either on one side or the other, about 8.85 inches away. Currents and thermal fluctuations, even minor drafts or temperature changes could create spurious education and scientific thinking, improving gravitational wave.
So back then we would use Cavendish's original torsion balance experiment, and the entire setup was housed inside a sealed mahogany box within a dedicated shed. Without disturbing, Cavendish would observe beam deflections through telescopes without disturbing the system. The forcing calculation at equilibrium the repetition for accuracy, he conducted 29 trials, adjusting positions and averaging results to reduce statistical and systematic errors. The challenges of this experiment: precision and angle measurements. Beam deflections were minuscule, measured with vernier scales to negative .01 precision. Oscillation noise required averaging and long-term observation. Why he did it. This was not accidental. He designed this experiment to reach a specific goal, which took extreme precision and patience. His motivation was driven by curiosity and a desire to test and confirm Newton's law of gravitation at a small scale. It was helpful with his precise method of using small forces also influenced experimental physics for generations. Some modern experimental processes, we would use a torsion balance with laser interferometry or atom interferometry. The atom interferometry, we used ultra-cold atoms in a vacuum. The mass is moved toward the atoms, and they measure the shift in the atoms to show gravitational attraction. Some of the differences in the modern approach than the old approach. They would do their calculations on a macroscopic level while we have to use it on atomic level. And they would have to manually write or analog their findings while we have digital sensors that can analog it for us. Some of the benefits of discovery was the ability for us to use satellite technology and GPS, and engineering and infrastructural design. Some of the future expectations of discovery are unifying gravity with quantum mechanics. Thank you.
He did the work. He wanted to determine the density of the Earth. No one at the time had measured tiny gravitational forces between objects in a lab. He was curious if it was possible to calculate such a weak mass and if it could be used to calculate the Earth's mass. This was not an accidental experiment because he designed it to reach a specific goal which took extreme precision and patience. The motivation was driven by curiosity and desire to test and confirm Newton's law of gravitation at a small scale which had not been done at this point in time. How it was helpful. It was immediately helpful at the time because it provided the first accurate value for the gravitational constant G and allowed scientists to calculate the mass and density of the Earth for the very first time. His work laid the groundwork for future advancements in subjects such as physics, astronomy, and engineering. His precise method of using small forces also influenced experimental physics for generations.